Welcome back, everybody. We're going to continue section 16.2 by talking about line integrals of vector fields. We're going to derive the idea of a line integral of a vector field by using work. Now in the book they talk about work as an application of this idea, but here we're just going to use work to derive it. If you'd like to see a more abstract derivation, you can take a look at the derivation in the book. So before we get to the line integral itself, let's remind ourselves in the context of vectors what work is. So if we have an object, the work done by a force on that object is the dot product of the vector representing the force dotted with the displacement vector of the object, or how much the object is moved. Now in the context of a curve, first let's just think of a single point on the curve. So let's think of this point here. These red vectors are going to be my vector field, my force vector field. These black vectors are my tangent vectors to the curve. And we're going to think of work in this context along the curve. For now, let's just think of the point. Work is going to be my f vectors dotted with the tangent vectors, because we want to look at the work along the curve. So at a single point, we just look at this f dot t. And that's the work at a single point on the curve. If we want the work done along the entire curve, then what we want to do is add up the contributions of every single point on this curve. So that's going to be an integral. We can define this the same way we define all integrals with a limit, but for now I'm going to skip that, and we're just going to integrate f dot t, where t is the unit tangent. And that's our line integral. ds, we're integrating with respect to arc length, and we're calling this work. But in fact, this is going to be the line integral of any vector field along a curve. So now, this is not how we compute these, so I'm going to go through a derivation of what we actually get. So we need to say that for this curve, we have some parameterization. We're also going to assume that this is a smooth curve, so that I can talk about the unit tangent vector using this parameterization, right? If I have a parameterization for this curve, then the unit tangent vector is the derivative of r prime divided by the magnitude of r prime. So that's why we need a smooth curve. We need this r prime to exist, and we need it to be non-zero everywhere, so we can divide by its magnitude. I can rewrite ds, the line integral with respect to arc length. We did this when we talked about line integrals last time. I can rewrite that as the magnitude of r prime dt. So now I've replaced the unit tangent with its definition. I've replaced ds with the magnitude of r prime dt, and then I just evaluate my vector field on the curve. Right? So the vector field, the domain might be much larger. It might be defined everywhere in x, y, and z. I just want to focus on the vector field as it's defined on this curve. Now as I simplify further, you notice that these magnitudes are going to cancel out, which is good news. When you take the line integral of a vector field, you do not have to calculate magnitudes like we did for the other kind of line integrals we talked about. So to calculate the line integral of a vector field, it's just f on the curve dotted with r prime. Now some other notation, you might see this notation where the line integral of a vector field is written as the integral over c, c is our curve, of f dot dr, where r is a vector, and this dr is just r prime dt. Okay, so now to summarize what we need in order for the line integral of a vector field to exist, we need f to be a continuous vector field defined on a smooth curve. So the curve needs to be smooth, meaning we can find a parameterization r where the derivative of r exists and is non-zero. And then we define the line integral of the vector field to be the integral from a to b, where a and b are the endpoints of our parameter values for the curve. F defined on the curve, f of r of t, dotted with r prime of t. Okay, now let's take a look at an example of this. So this example says calculate the integral over c of f dot dr, where f is negative 1/2 x, negative 1/2 y, 1/4. This is my vector field. And c is a helix given by cosine of t, sine of t, t, from the point 1, 0, 0 to the point negative 1, 0, 3 pi. Okay, so if I look at the formula, I know what f is, I'm given r, I need to figure out what f on r is, I need to figure out what r prime is, and then I integrate from a to b. Well, the first thing is, I don't have an a and b. So we need limits for the parameter t. T is the parameter of our curve. I need to know where this curve starts and where it stops. I have point values, 1, 0, 0 and negative 1, 0, 3 pi, but I need to know what values of my parameter t give me these 2 points. I know this needs to be my starting point, this needs to be my stopping point. So I've written here that t goes from 0 to 3 pi. Why is that the case? Well, you can set up a system of equations where you say each of these components equal to these points and solve for t, but you notice the z component of our curve is exactly t. So this z component of these points is telling us what t values we're starting at and what t values we're stopping at. So there's a little trick there for this one. Alright, now our integral is going to be the integral from a to b, 0 to 3 pi of f of r of t and r prime. So now let's see what these two things are. F of r of t, so I'm plugging the curve into my vector field. So everywhere I see an x, I'm going to replace x with cosine t. Everywhere I see a y, I'm going to replace y with sine t. And everywhere I see a z, I'm going to replace z with t. That's how I plug this curve into my vector field. Well, I don't have any z's in my vector field. I just have one x and one y. So my vector field becomes negative 1/2 cosine t, because I had negative 1/2 x, and now x is cosine t. The second component is negative 1/2 sine t, because I had negative 1/2 y here, and on my curve, y is given by sine t. And the third component's constant, it's just 1/4. And again, we're using this curve to see what we plug in for x, y, and z. Now, I need to take the derivative of r, which should just be a simple thing. R prime is negative sine t cosine t 1, just taking the derivative of this function. And now I have everything I need. I can set up my integral. So the line integral of this vector field along this helix is the integral from 0 to 3 pi. These numbers are coming from the interval where I'm taking my parameter values. Here I have f on my curve, negative 1/2 cosine t, negative 1/2 sine t 1/4, dotted with r prime, negative sine t cosine t 1, dt. Now to evaluate this integral, I need to compute this dot product. Remember, the dot product is a scalar, so once I compute this dot product, it's just an integral that I might have seen in Calc 1 or Calc 2. So when I compute the dot product, I multiply corresponding components, so negative 1/2 cosine t times negative sine t gives me 1/2 cosine sine, plus negative 1/2 sine t times cosine, so that's minus 1/2 sine cosine, plus 1/4 times 1, which is 1/4. So this is nice. These two terms are going to cancel out. I'm left with 1/4. And so really, I'm just integrating 1/4 from 0 to 3 pi. So that's 1/4 t from 0 to 3 pi. That's 3 pi over 4. And that's our line integral. So geometrically, is there anything we can talk about for these line integrals of vector fields? And yes, the sign of our answer tells us something. So for this example, we had a positive answer. What can that tell us? Well, let's say I have this curve C, and my integral is positive. What that means is that the forces of my vector field, my f, are going the same direction that my curve is being traveled along. So here my curve is being traveled along in this direction. I have an orientation. It's going this way. In general, these vectors are pointing the same way. So this is positive. If all of my vectors, my f vectors, are orthogonal to the curve, then it's going to be 0. And if my vectors in general are pointing the opposite way that the curve is being traveled along, then my answer is going to be negative. And this this matches with what we know about the dot product. If you go back to chapter 12, when we first introduced the dot product, we said that if the angle the two vectors make in your dot product is acute, it's less than 90 degrees, then your dot product is positive. So that's what's happening here. You can think we're dotting these blue vectors with tangent vectors that are going this direction, because that's the way we're traveling along the curve. So those are small angles. Here they're 90-degree angles, so it's 0. And if you have obtuse angles between 90 and 180 degrees, then your dot product is negative. And that's what's happening here, because our tangent vectors are still going the same direction as the curve. Now something else can happen to give us 0, right? Let's say that I have a mixture of arrows pointing, or vectors pointing the direction of the curve and pointing backwards along the curve. They can balance out and give you a 0 as well. So if your integral is 0, that doesn't mean that your vector field has to be orthogonal to your curve. You could have things balancing out and giving you 0 as well. So when we talked about line integrals of scalar functions, we said that the orientation of our curve doesn't matter. The way we travel along our curve didn't matter. We could travel either way, we'd get the same answer. But now that we have vector fields, we can see this is not the case, right? Because if I were looking at this example where we definitely have a positive line integral, and then I start traveling along the curve backwards. So instead of going this way, I decide to go this way. Well, if I travel along this curve backwards, now all of a sudden these vectors are pointing against me. They're pushing me against the way I want to go. So my answer would become negative. So the orientation of our curves is important. If we change the orientation, we change our answer. And all it does is changes the sign of our answer. So if the orientation of your curve changes, the sign of the integral changes. So here I'm using negative c to mean that we're traveling along the curve in an opposite direction. So the integral over c of f dot dr is minus the integral over negative c, the same curve, just traveled backwards, of f dot dr. So that's something we need to be aware of. One more thing before we go. I can represent the line integral of a vector field in another way. Let's say I write f in terms of its component functions, p, q, and r. These would be functions of 3 variables. And I look at a parameterization of my curve. Then I can take my line integral of a vector field, and that's going to be pqr defined on the curve, dotted with the derivative of r, which can be represented by x prime, y prime, z prime. And if I compute this dot product, I have the integral over the bounds for this curve, which I didn't write, but they're going from a to b, of p on the curve times x prime, plus q on the curve times y prime, plus r on the curve times z prime. And here we've just computed a dot product. That's all that's happened. But now I'm going to distribute this dt. We're integrating with respect to t. I'm going to distribute this dt to each 3 of these terms, and I'm going to define new differentials. So if I distribute dt, I'm going to call x prime dt, x prime of t dt dx, call y prime of t dt dy, and call z prime of dt dz. And so you might see this notation in the book or in examples or in problems that you're asked to work. This is the same thing as the line integral, like the example we just did, but this notation is just doing the dot product for you. So this is the line integral of a vector field where we're integrating with respect to x in the first component function, integrating with respect to y in the second component function, integrating with respect to z with the third component function. But these x, y, and z actually describe the curve. So they're x prime, y prime, z prime of the curve. Okay, and we'll talk more about this in the next video.